After a bit of a more general start to the day, we're back to core business of melting the mantle. It's my pleasure to introduce Sam Butler from the University of Saskatchewan, who's going to talk about melt shear bands, and really excited to hear what they have to say. Thank you.
Okay, is the mic working?
Yep.
Okay, good. All right, well, thank you, Tobias. And I'd like to first thank all the organizers of this workshop and this meeting. I've learned a lot. I think it's been really stimulating. So what I'm going to be talking about are these things. Now, we've seen this image, quite a few times. But so in a paper in 2003, Holtzman et al. Showed that in these experiments that you can see are, this scale bar is like 500 microns, so they're sort of small lab-sized experiments. What they showed is in these samples that initially had a pretty much a roughly uniform porosity, after they'd undergone a significant shear, the porosity separated into these bands. You can see here these dark features here. Those are bands where the porosity is significantly elevated over what it was initially. And then the light regions in between are regions where the porosity is significantly less than it was originally. Okay, so there's this phenomenon that spontaneously segregates the porosity. Okay, and so here's one of my simulations. So there's been a bunch of theory and numerics done on it. And so what I'm going to be talking about is just some of the different efforts that have been put into sort of reconciling these things, and then also understanding what effects these might have in the Earth's interior. Okay, so also just to emphasize, these things are pretty small. And so there's a scale length that I'll talk about in a minute called the compaction length that we've heard about already a few times in this, but I'll review it quickly. But we think roughly scales the size of these things. So obviously if you had structures this big in the mantle, they probably wouldn't be too important, but the compaction length in the mantle is many times bigger. It's probably sort of the tens of meters to a few kilometers. Okay, so one of the implications that these might have, and this is an idea that Rich and Mark Spiegelman in their paper in 2006 pointed out, is that if these bands have a nice orientation such that they're pointed towards the ridge axis, then they might act as a conduit. There's a high permeability conduit to help move melt towards the ridge axis. So as we've heard already a number of times, there's this issue as to how is melt transported laterally beneath the mid-ocean ridge, okay, and how does it move relatively quickly? So that's one possible implication. Okay, another is that if you've got these melt bands, and actually maybe I'll go back to the image where we had one here. So if you've got these high porosity bands here, so the viscosity is going to be presumably significantly less within there. Okay, and so you could get strain localization. Okay, and that's actually seen in some of the experiments where you've got a strain marker. There is strain localization going on within the band. Okay, and so if that's happening, then you're lowering the effective viscosity of the whole thing. Okay, so in other words, the work that you're doing to keep deforming here might be significantly less than it would have been. Okay, and so the effective viscosity could be less. Okay, and so that also, if you've got these chunks of material where the effective viscosity is less, that could have some, implications for, the deformation in the upper mantle. Okay, and so here's the effective viscosity from one of these experiments as a function of the shear throughout the experiment. You can see it has dropped. Okay, another one. So we've seen, Shun showed this image yesterday. So this is the results of inversion of magnetotellurics. Okay, and so what it shows is this region of where the electrical resistivity is lower beneath the plate. Okay, and so also what's shown down here is that the electrical resistivity is lower in this direction than it is in the direction in and out of the plane of this figure. Okay, so that's consistent then with sort of a tube of melt along here. So these aren't necessarily exactly these bands, but if you did have a band that was oriented in a particular direction, that could act, again, if you've got these regions of high porosity, they will also have high electrical conductivity. Okay, so they also then could be causing this sort of variations in electrical conductivity and its anisotropy. Okay, and then so lastly, it also was proposed in this paper by Holtzman and Kendall in 2010 that the bands, if you've got these large structures, they could also affect the observed anisotropy of seismic waves. Okay, so those are some of the things, some of the reasons why, as geodynamicists, we should care about these. Okay, so What's nice is we do have the experiments, then we have the theory, and so there's some comparison. We can make comparisons between the theory and the experiments. So one issue that's received a lot of attention is the angle of the bands. Okay, so if you look at these bands, see the dark features here, you can see that they're roughly at 20 degrees from the shear plane. Okay, and so a lot of work has been put in to try and get that. It's been shown that the bands, at least if you've only got a purely porosity-dependent viscosity, they'll grow fastest parallel to the direction of maximum compression, okay, which in a simple shear flow is at 45 degrees. Okay, and then because of rotation by the background flow, they'll go to even higher angles. Okay, and so the question is, well, how do you get that lower angle? Okay, and so a few different things, different rheologies have been put forth that you can, where you can change the orientation of the bands. So one is strain rate dependent. Okay, so Rich first looked at that in 2006, and in fact you can get these fairly nice low angle bands that way, but you need a very large strain rate exponent. Another issue is that some of the experiments definitely were run where the viscosity was not in a strain rate dependent regime, and yet they still got the low angle band. So there must be something going on. Okay, another idea is this anisotropic viscosity. Okay, so Yasuko and Van Holtzman had papers in 2009 where they basically looked at the fact that when you sheared a sample like this, you also get alignment of melt at the grain scale. Okay, so not only do you get these sort of quasi or these macroscopic bands, but you also get little melt pockets oriented based on the stress field at the grain scale. And so that will affect then how the material can deform. Okay, and so they came up then with a whole theory for anisotropic viscosity. Okay, and so I've done some modeling with the anisotropic viscosity. I know that Rich's group has also done quite a lot. And yes, if the melt bands are in an orientation such that they themselves, excuse me, not the melt bands, but the melt pockets are in an orientation such that they themselves are parallel to the direction of maximum compression in the experiments, then you can also get these low angle bands. Okay, and then more recently, John and Dave have published a paper where you've got grain size dependent viscosity and some damage rheology. Now it turns out in a certain limit, those actually end up essentially looking a lot like the strain rate dependent viscosity ones, but you can also get these low angle bands that way. Okay, so another issue is the width of these bands. Okay, so what's interesting about them really is that they're macroscopic, right? So they're not staying at the grain scale. And yet, as I'll show in a minute, if you do the linear stability analysis on these things, they should actually grow fastest at 0 wavelength, right? And so which implies then that they should never get any wider than the initial heterogeneity scale. Okay, and so I'll look at why that is, or how they might get wider. Okay, a few other things. Some of the experiments seem to indicate that you don't get these bands forming if the compaction length, or excuse me, if the sample is small compared to the compaction length of the material. Okay, whereas in the theory there actually isn't anything to prevent them from doing so. So that's actually, I'm not unfortunately going to address that any further, but that's another issue. And then the other one is a sort of the end condition. Okay, and so one of the somewhat embarrassing things, at least in my numerical models, is they end when they crash, essentially. So that, there's something going on wrong. The rock doesn't crash, right? And so there's, there's something there that we need to think about, and what happens and what stops the instability before disaggregation occurs and things like that. Okay. So the outline for the rest of the talk, I'll do a little bit of a background on compaction theory. I know a lot of experts are here, but I hope this will still be useful for some people. I'll then go through the theory of melt band formation. I'll talk a little bit about linear theory and numerical models. I'll look a little bit at the effects of buoyancy on melt, because that's one of the things that I've looked at. I'll try and answer this question of why are the bands wide. I'll show some simulations with bands and a damage rheology. And then I'll also look at the orientation for melt bands in a min-ocean ridge corner flow. Okay, that's another project I've been involved in. And then at the end, I'll show some attempts at looking at sort of effective viscosity and effective electrical conductivity. Okay, so compaction theory, we've seen these equations lots of times. These were first written down by Dan McKenzie in 1984. So I've non-dimensionalized these based on time comes from the strain rate and based on the compaction length. Okay, so I have included the buoyancy effect here. So you've got essentially a Darcy law for the separation of the fluid. I've written as the little u. From the solid matrix, I've written as capital U. Okay, you've got a force balance for the solid. So again, I've kept the buoyancy effect here. It's pretty close to a Stokes fluid, but of course there's this bulk viscosity term here. Now there's different ways of doing this depending on whether you break up the pressure in different ways. I've just left the pressure as just the liquid pressure. Okay, so then in terms of mass conservation, you've just got that the combined volume is incompressible. Okay, and then the evolution equation you have then comes from the conservation of the solid phase. Okay, and then in terms of looking at these bands, then we also need a relationship for the permeability. So I just assume a power law, and I take the power law exponent to be 3 in all of these. Okay, in terms of viscosity, you then also need a viscosity law. Okay, so what's crucial to form these bands is that the viscosity decreases with the porosity. Okay, so this is this exponential variation of the viscosity with porosity that's based on experiments from the Kolstad group in Minnesota. Okay, and actually I've written this down here for also having a strain rate dependent viscosity as well. I'm not going to include that in all of these. And also I will look at some with the grain size dependent later on. Okay, so just to show sort of some of the very basic stuff involving compaction theory. So the compaction length is given by this quantity here. So the permeability divided by the fluid viscosity times the solid viscosity term, well, the bulk and the shear viscosity describing the solid matrix. So one way that I like to think about it, and taking the square root, of course. So one way I like to think about it is this this part here tells you how easy it is to move a fluid, right? And this part here tells you how hard it is to deform the solid. Okay, so what happens then is that if you've got a sample that's big compared to this, you'll get significant deformation in the solid, right? And if you've got a sample that's small compared to that, you'll mostly just get motion of the liquid. Okay, so I'll just show, these are actually just a couple of quick simulations. So in this case, there's no shearing going on here. I've just set up a column that's got gravity, okay, and so they've got impermeable boundaries top and bottom. And so if the system is big compared to the compaction length, so this is scaled in the compaction length, you can see what happens is that the porosity accumulates at the top because the melt is moving its way to the top, okay, and there's actually unnecessarily 2D. These could have been 1D, but that's what I had. Anyway, and then the other thing you can see is that the boundary layer thickness is of order the compaction length. Okay, so just to give people some intuition on this. Okay, if your sample size is way smaller than the compaction length, in this case, on the same time scale, nothing happens. Okay, it's sort of boring to see a video where nothing happens, but I find it illustrative anyway. Okay, so how do these melt bands form? So what I'm going to go through is essentially the argument that David Stevenson had in his late 1980s paper, only with color pictures and videos. So how does this work? So what I'm going to do is I'm going to consider now there's no buoyancy, okay, and I'm going to assume just a pure shear flow. Okay, so fluid's coming in, the solid matrix is flowing in from the bottom and down from the top, and it's flowing out onto the two sides. Okay, so I've got a pure shear flow. Okay, and so what I've done then is the colors here are indicating the viscosity. Okay, so I've then just put a circular Gaussian perturbation to the viscosity. Okay, so if we think about what's happening here, if you think first, say, about the force balance in the vertical direction, okay, so the motion of the matrix is dominated by the background pure shear flow. Okay, so it doesn't have any tangential components. Okay, and so if you take the divergence of the stress tensor in the vertical direction, it's just going to be d by dy of the normal component in the y direction. Okay, and so since that's 0, that tells us that the normal component of the stress in the y direction is constant. Okay, so it's or pretty close to constant. Okay, so actually ignoring the compressible part of that, because that's also going to be small, at least early on, you've got the following for the vertical component. Okay, and so you can see that dv by dy in this type of flow is negative, right? Because it's positive down here and negative up here. So the velocity is positive down here and negative up here. So the derivative is clearly negative. So what happens then is if you compare, say, what the pressure must be in order to keep things constant. say down here as opposed to here in the middle of the perturbation, you can see if dV by dy is essentially constant. Okay, if eta is a little bit smaller, okay, in order to keep tau y constant, you have to have the pressure be a little bit higher here than it is down here. Okay, and similarly, it has to be higher here than it is up here. Okay, so you're going to get, so those pink arrows are showing the direction the fluid's going to flow as a result of this. Okay, and if you do the same thing in the horizontal direction, you go through the same argument, except that the du by dx is positive. Okay, and so as a result, you're going to get a difference in pressure from inside the perturbation to outside. So the pressure is going to be smaller here than it is out here and out here. Okay, so as a result, fluid's flowing in here and here. It's going out here and here. Okay, and so you can see so then what happens, a couple other extra points. Because the fluid's going to accumulate here because of flowing in from this way, because it's a compacting system, that's actually going to decompact. Okay, so you're going to open up pore spaces in here. Okay, as a result of opening up pore spaces, if this is the viscosity law, if the viscosity decreases with the porosity, the viscosity is then going to decrease. Okay, and so you already had this low viscosity region, you're then making it even lower, which then makes the fluid flow into it even more, and then you've got this positive feedback loop and you get a runaway instability. Okay, and so to see videos illustrating that, so what I've done on the left here, this is a case I've just got, this is a porosity perturbation, okay, I subject to a pure shear flow. Okay, in the first case, I've turned off the porosity dependence of viscosity. Okay, so just to see what happens, or just so we can compare it with the other one. So here I've got these strain markers of the white, okay, and so essentially what all that happens is that the porosity gets advected by the background flow. You just sort of squash that perturbation, nothing terribly interesting. Okay, so now we'll contrast that with what happens when the viscosity strongly decreases with the porosity. And you can see it's quite dramatically different. Right? So you get this band forming, okay, and it's parallel to the direction of maximum compression, and I had to let the color bar rescale just to keep it all, such that you could see anything. Okay, so that's sort of how it works. So now I'll just look at strain rate dependent viscosity. So now if you have the viscosity depending on, in this case it's written down here, it goes, or this epsilon 2,2 is the second invariant of the strain rate tensor. Okay, so what will happen now is that the background velocity, so that du by dx and dv by dy will be in here. Okay, and that will multiply times the tangential components of the strain rate. Okay, and so what happens then is you will then get some component then that's, or what ends up happening is you get a splitting, essentially, of the directions where you'll be growing these bands the fastest, okay, because of that coupling. And so then, depending on the strain rate exponent, you will get bigger and bigger splitting. Okay, and so you get similar effects for anisotropic viscosity. You again get coupling between the background flow rate components or between the tangential and the normal components, and so you also get sort of splitting in that case. Okay, so I'll look a little bit at the effects of waves. So one of the things I was interested in is, well, do you still get these things if you've got buoyancy going on? And so one of the neat things in these compacting systems is they make waves. So again, here I've just got a couple of illustrative simulations. So in this case, I've got fluid that's being injected in the bottom of this column. Okay, and it can go at the top. Again, there's no shear going on in these. Okay, but it's being injected at just such a rate that the stress that it's exerting on the matrix as it goes through is just enough to keep it supported. Okay, and so we can see what's going to happen is nothing. Okay, whereas in this case we've got a vertical variation in the porosity, which is going to change the permeability. And now you can see you've got waviness going on. So essentially what happens is where you've got a change in the permeability, the fluid can shoot ahead, okay, and so in some region behind that, then you'll get a decrease in the porosity that'll decrease the permeability, and then fluid will build up behind that, and which will open up the porosity. And so you get this sort of waviness going on. Okay, so I'll now just look I won't go through the details of the linear theory, because that would take quite a long time. But essentially what we do, or what's done, and this was, I certainly first saw this in a paper by Mark Spiegelman in 2003, where he looked at the linear theory for purely porosity-dependent viscosity. So essentially what you do is you take these plane waves, okay, and so the orientation of the plane wave is controlled by the relative size of kx and ky, right? And so you expand the porosity in these plane waves, and then you look at whether they will grow or decay by whether, S is positive or negative, and how big ds by dt is. Okay, and when you include buoyancy, you also have this imaginary term. Okay, and so you can go through the theory and you work out, at least for a strain rate dependent viscosity, you get these forms for the pure shear and for the simple shear. And actually they're exactly the same thing, just rotated by 45 degrees as they should be. So just a couple of things that we can get out of it. So one is that by including the buoyancy, you notice here it only really affects the frequency of oscillation. Okay, so it's not affecting the growth rate. So the buoyancy number here is just coupled to the oscillations. A couple other things to see is that if you work out the angle at which these things will grow fastest, if you set n equal to 1, so if it's not strain rate dependent, you recover that they grow fastest when they're parallel to the direction of maximum compression. You could also look at the wavelength, so through these k's, okay, and so one of the things you can see is that if k becomes really big, what ends up happening is that the growth rate essentially becomes independent of the wavelength. Okay, so that corresponds to the wavelength being really small. But in fact, it's peaked for 0 wavelength. Okay, so just a quick summary of that. That's essentially what I've just said, I guess. But what ends up happening if you look, say, at a pure shear where you're compressing vertically and stretching horizontally, is the bands will grow all the time if they're sort of between this orientation and this one. They'll decay in this area. Okay, and then depending on the particular rheology law, they'll grow fastest at some angle within here. Okay, and in simple shear, it's the same thing, just rotated by 45 degrees. Oh, and one other thing I wanted to point out with the oscillations is that they oscillate fastest, okay, if you've got if they're horizontal, and they don't oscillate at all if they're vertical or parallel to gravity. Okay, so my model, I'm not going to talk an awful lot about it. So in the pure shear cases, actually what I do is I actually impose periodic boundaries actually on both top and bottom and sides and the two sides. Okay, and also that allows me to do some of these buoyancy cases. Okay, and I solve these in finite elements using COMSOL multiphysics. Okay, so here's an example starting with just a random heterogeneity field for the porosity. Okay, so in this case I'm squeezing it vertically, okay, and stretching it horizontally. So this is one of these pure shear cases. Okay, and it's not a strain rate dependent viscosity. Okay, and there is actually a lot of buoyancy in this case. So in this case, you can see here we got these bands forming, and they are parallel to the direction of compression. Okay. Although there's a lot of buoyancy, you don't see a lot of wavies in there. Okay, and the reason is because the bands are essentially vertical. Okay, and so there's not a lot of vertical variations in the permeability. Okay, whereas here you can see a dramatically different case. Now I'm going to squeeze it horizontally and stretch it vertically. Whoops. Okay, and you can see it waves like crazy when I form the bands horizontally. Okay, and so now I'm just doing one other case here where I've got a strongly strain rate dependent viscosity. Again, it's going to wave a lot, but we'll see kind of what it looks like at the end. So you can see we've got these two orientations of bands forming, this sort of one like this and one like that. Okay, because we've got these two directions for growth rate that you get when you've got this strongly strain rate dependent viscosity. Okay, so one of the things that's nice to try and compare the linear theory and the numerical model, just so we hopefully can have some confidence in the numerical model. So that's what I've done in this case here. So in this case, I just started a numerical model with plane waves. Okay, and so now the theory, when you work out the theory at least easily, you actually do for the case of an infinite domain. So this is a finite domain, so it's not going to be absolutely perfect. But what I did is I started with a plane wave, and I just look actually at this case, I'm just plotting what the porosity, actually the log of the difference in the porosity from its initial value right at the center of the domain. Okay, and so what happens then, so what I've also plotted here, the dashed line is basically from the growth rate, or it's by integrating the growth rate for the linear theory. Okay, while the dotted line is by integrating the growth rate for the linear theory and including the oscillation term. Okay, and so these cusps basically come about because it's going to go through 0. right? But I'm taking the logarithm of the absolute value. Okay, so you can see then the solid black line is what the numerical model did. Okay, so it agrees quite nicely, which is comforting. And so then I also did some cases with different strain rate dependencies of the viscosity. Okay, and so this is one, and now actually the fact that these are different is I just displaced them so they could be put on the same figure. Okay, so the fact that this starts at -5 is not of significance. Okay, so what happens though with these is you can see that they actually, the linear theory predicts that they actually will start to decay at some point because the bands get rotated by the background flow, and eventually they'll go to an orientation where they'll start to decay. Okay, so in the linear theory there's nothing to stop that happening, and they'll just start to decay over this way. But in the numerical model you can see that they oscillate and they grow and then they just keep on growing, right? And it's the same thing happens for this larger one. So essentially what's happening is that you've got bands, you start to nucleate new bands essentially. Okay, and so that are in a good orientation for growth, and they just keep growing past that point. Yep?
There's a sort of medium wavelength of oscillation, and I wondered if that has to do with successive generations of bands that...
Yeah. No, I think that's probably right. Where we start, not agreeing so well with the linear theory, I think that's where the nonlinear effects are kicking in, and we're starting to get a new generation of bands forming. I think that's probably right. Okay, so just to think a little bit about whether these things are important, or whether the oscillations are important in a mid-ocean ridge. So I calculated my buoyancy number, and I just in a corner flow model taken from the Spiegelman and McKenzie paper. And so the black contours are the buoyancy number. Okay, and so you can see for a good chunk of the mid-ocean ridge environment, yeah, the buoyancy number is actually going to be significant. So it's probable that they are important. Now the question is the growth rate or the angle going to be significantly affected? And so my calculations seem to show no. Okay, so what I'm plotting here, this is what I call the amplitude. So it's essentially the root mean square of the porosity integrated over the domain. Okay, so it tells you essentially how much the porosity has changed from its initial value. Okay, and so the black dotted lines are the predictions of linear theory. Okay, and then the various other lines are the numerical model runs, but with different values of the buoyancy. And you can see that in all cases they grow at essentially the same rate. Okay, and so this is the end of one simulation with a high degree of strain rate dependence. And you can see you get the nice low angle band. So this is for very low buoyancy. This is for quite high buoyancy. Okay, you can see you get the nice low angle band in this case, but this case actually you can see you get actually the high angle bands again. Okay, and so I think what's happening is that because you've got these oscillations going on, you've got sort of these new sort of blobs forming all the time, and so there's new directions essentially for the bands to keep forming on. And so that keeps these high angle bands around, even though, in this case they get rotated by the background flow into an orientation where they would decay. Okay, so in terms of the effects of buoyancy, so at least I find that the buoyancy does not inhibit the band growth. Oh, and actually one other thing I wanted to point out in the last one is that these pink arrows are showing the direction of fluid flow. Okay, and so this is right at the end of that simulation when it was about to crash. And you can see, though, that the fluid is now really being significantly influenced by these bands, right? The permeability structure is influencing it. And it's only right at the very end that happens, actually. So these arrows otherwise are essentially going vertically. And I'll show other examples. Things are just starting to get interesting, and then the model no longer works.
Did you say they crashed because you reached zero porosity somewhere?
I think, yes, that is. Actually,
porosity is not on the limit yet, right?
That's right. Yeah. Now, these are some of my old simulations where I actually didn't constrain the porosity at all to be, so it could go negative even in these ones. And actually, I think you can see this is the min porosity here, so it was slightly negative at that point. Yeah, so I seem to find that the bands don't inhibit, the buoyancy does not inhibit the band growth. And I know that Rich has some models of a corner flow in a mid-ocean ridge that does have compaction and does have buoyancy, and the bands didn't form. So there's I think, something we need to look at there, yeah?
Can I just ask you to go back to the previous slide?
Sure.
Okay, I mean, it's a simplified geometry, but yeah. I think a bigger question is whether it's reasonable to have periodic boundary conditions in the y direction.
Yeah.
Because, of course, in the mantle, well, it's not periodic in the y direction, and bands wouldn't be formed below the depth of the domain. So would it be more reasonable to have an inflow and an outflow condition, and the inflow is uniform porosity? And if so, did you...
No, yeah, that's a good point. That's an interesting point.
That really does have a huge effect on the results.
Yeah, no, that's true. That is certainly true. But I guess, if you look higher up in the melt column, you'll have bands that have come up from some depth below there where, there will be heterogeneity coming into the volume as well. But yeah, you're right. I could try something like that and see how much that affects things. Okay, yeah, that's what I was going to say here. So now, why are the bands wide? Okay, so so I'll just emphasize here. So this is an image down at the grain scale. Okay, so you can see these melt pockets. But the thing is, that's not what we're looking at with these bands. We're looking at these sort of more macroscopic bands. Okay, and so really, what's interesting is that we do get these bands at this sort of macroscopic scale. Okay, and so in these papers by Kolstad and Holtzman, they also plotted spacing between the bands as a function of the compaction length in their experiments, and they seem to show that there is a scaling between those two. So it seems as though the compaction length is controlling the spacing of the bands. Okay, but as I pointed out before, this is a curve just showing the growth rate for different strain rate dependent viscosities, and you can see that it's peaked at 0, right? So as I was explaining before, it seems odd that the theory would seem to predict that you should never get anything forming that's of larger spatial scale than this. It should just stay at the initial heterogeneity length scale. Okay, but if you look at the numerical models, they also do start getting wider. Okay, so here's a simulation I did. It actually goes on a long time, so I'm going to skip ahead. You can see midway through, you've got some banding going on, and you skip towards the end. You've got banding still, but you see they're a lot wider by the end. Okay, and so actually here's just an image from midway through and by the end, and you can see that the length scale spectrum clearly is a lot bigger in this than it is over here. Okay, so something in the numerical models is making the bands wider, even if in the linear theory there isn't. All right, so here's my explanation, and it is based on the advection of the bands by the background flow. Okay, so what I'm considering here, these are just bands, and I'm going to show their evolution just by advection. Okay, so there's no compaction going on. Okay, in this case, I'm looking at a pure shear flow where it's being compressed vertically. So one of the things you can show then is that the band evolution. So one of the things that happens in the linear theory is you have these time-dependent wave numbers that get rid of the advection term essentially, and so in a pure shear they go exponentially. Okay, and what happens then is that in you can see that the wavelength in the the wavelength in the x direction will actually increase exponentially with time. Okay, so if we look at what this does, okay, so I started with a band that's this way, and it's going to slowly rotate down this way. Okay, so it slowly gets fatter, right? And remember that it grows in amplitude till it's about 45 degrees, which is there. Right, but then if you rotate beyond that, it gets skinnier. Okay, so at least for these pure shear ones, if they're in an orientation for growing in amplitude, they're also getting fatter. Okay, and if you look at simple shear, it's a similar thing, right? So remember that for simple shear, they will grow until they get vertical, and then they'll start to decay when they go beyond vertical. And, I'm losing, okay. So you start here, you can see they get wider, 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 and then they start to get skinnier, skinnier, skinnier. Okay, so similarly in the simple shear geometry, they get wider when they're in a direction for increase in amplitude, and skinnier when they're in an orientation to decrease in amplitude. And in fact, if you do just so it's nice in a pure shear in that you can sort of get rid of the effect of rotation. If I just start with these perfect vertical bands, over time they just get wider. Okay, and this is just showing the wavelength spectrum, and it's quantized because I'm using periodic boundary conditions. But it gets wider with time, and actually you can't see it well, but there's an exponential on here that fits pretty well. And actually another thing I found is that if you turn on buoyancy though, so if you've got these horizontal bands that are waving like crazy, they actually don't increase much with wavelength, or much in time. Essentially, I think because we just keep sort of creating new ones. All right, and so what I did here is I started a bunch of simulations with different initial heterogeneity wavelengths. Okay, so I just made them, so these were the finest, and they got coarser, coarser, coarser. Okay, and so you can see what happens to the wavelength as a function of strain, which is the same thing as time in these cases. Okay, so the wavelength goes up, and then it seems to kind of saturate here around 0.8 times the compaction length. All right, and so if we start coarser, it goes up again, but again, it saturates around 0.8 times the compaction length.
Is random fields or bands imposed?
Those were random fields, yeah.
What frequency content did you put in to begin with, your random fields? How have you done your randomness?
So the randomness, in this case, what I did to get, say, these ones, is I actually went to I created a really coarse mesh, and then I created a random field on that coarse mesh, and then I just interpolated it onto a finer mesh. So that's, these different generations, that's, yeah. Yeah. And actually this one down here was one that had buoyancy in it, and you can see it didn't grow in wavelength as quickly.
What are the strains in the experiments? I can't remember.
The total strains, they can, I think, well, they start to see bands, or I guess they start to report them around 1. Some of them went up to sort of 2, I think, or 3. I think it's sort of that kind of.
The simple shear experiments go to at most 2, 3, but the torsion experiments can go up to 10.
Okay.
I mean, in theory, they could go higher.
Yeah. Okay, so anyway, that's my explanation, at least for in the numerical experiments, why the wavelengths get larger with time. Right, I know that John and Dave have a paper recently looking at how so certain effects of surface tension can also cause the bands to have a macroscopic size. But you can see that the numerical experiments also show that they're wide and they don't have that surface tension physics in it. Okay, so I think my explanation at least is explaining what's going on in the numerical experiments, even if it's not. I mean, we don't know for sure then that that's what's actually happening in the physical experiments. Okay, so I'll just show now some newer results. So so John and Dave also had this paper looking at damage rheology, okay, and these bands. So I thought, well, I'll take a look and see what I can do in terms of modeling that numerically. So the idea with the model is okay, we've got these grains, okay, that's with the capital R is measuring the size of the grains. Okay, and there's a certain roughness that's characterized by this little r, which is the radius of curvature, essentially, of those. Okay, and so so that varies the viscosity law. Okay, so the grain size, or the viscosity depends on the grain size. It also depends on the roughness, or this r radius. Okay, and then there's the evolutions the evolution equations for the roughness and the grain size look like this. Okay, so essentially we've got growth going on of this r. Okay, but then it also can basically what's really important here is actually this capital psi, which is the rate of viscous dissipation going on. Okay, so work basically is causing a decrease in little r. Okay, so it's making sort of shorter wavelength or variations on the size of the grains. Okay, and then there's another evolution equation for the grain size. Okay, so again, they can grow in time, and then there's a pinning term that depends on the roughness. Okay, so in these later ones, I actually put in a transformation of the porosity to keep it from going to 0 or above 1. Okay, so there's a transformed porosity that can go between minus infinity, but with this hyperbolic tangent, it's forced to be between 0 and 1. It seems to allow the simulations to run a little bit longer, although not a whole lot. Okay, so some of the constants then that go into this, so there's the m and n parameters that say how sensitive the viscosity is to the grain size and to the roughness. Okay, and so for grain boundary creep, that's 3, and that's actually all the ones I'm going to show here. For volume creep, it's 2, and then the other thing is this parameter n. So we can either have the viscosity be completely insensitive to little r, or we can increase it. So essentially, that characterizes sort of an increase in viscosity, sort of due to the sort of roughness of the grains. And then there's these growth rate parameters, okay, which John and Dave estimated to be in this range. Okay, and so one of the things that happens, so essentially, or I'll show them the next slide. So they worked out the linear theory. This is their linear theory. One of the things that happens, though, is if these growth rate parameters are really big, essentially what that does is it forces both sides to be zero of the equation, and so you get back a grain size, or excuse me, a strain rate dependent viscosity, essentially because of the deformational work essentially is a lot like the strain rate, okay, and so you get a strain rate dependent viscosity that, the coefficient goes like this, okay, and you get an effective porosity weakening that also goes like this. So going through the linear theory, basically you've got this matrix A that they derived, and you can look at the eigenvalues of that matrix, okay, and so the instability will grow at the largest positive value of the eigenvalue, okay. So here's the results of one of my simulations. Okay, so here's a case where it's grain size dependent, but not roughness dependent. Okay, and see here I've got the time scale for the adjustment of the roughness to be sort of similar to the strain rate. Okay, and so this is near the end of the simulation. So this is the porosity field. You can see I get these nice bands. We also get bands in the roughness that are actually correlated with the porosity bands, but then the grain size is actually anti-correlated. Okay, we've got actually the opposite polarity for the grain size bands. So that would predict then that within the high porosity bands we should be seeing small grain sizes. Okay, another thing though that you can see is that although what I'm showing here is the amplitude, so again I've integrated the root mean square of the porosity, the roughness, and the grain size and plotted those. And I've also plotted the prediction of linear theory, so they're a little bit less than linear theory predicts. But the other thing is though is that the localization of all three fields increases at a similar rate. Although the highest porosity you can see is quite a lot higher. I started this one with a 0.05 porosity. So here it's roughly doubled by the end of the simulation, whereas you can see that the roughness and the grain size have only sort of changed by 25% or so. All right, and so here I'm just looking at what happens when you change this gamma parameter. So if as the adjustment gets faster, you do actually, it has a significant effect on the orientation of the bands. It goes from these unfortunate or these fairly steep angle bands to pretty shallow ones as you increase this gamma parameter. So this is just showing the angle spectrum. So it's just showing as the power moves to lower angles as you go up. So basically the faster you can adjust, so the more you move towards purely a strain rate dependent viscosity, the more you get the low angle bands. So unfortunately at these lower, these cases where it's not just behaving like a strain rate dependent viscosity, the bands tend not to be at the nice low angles. Okay, and so here I'll just show the evolution of one simulation with the porosity, the grain size, and the roughness. So this case, so this is a case where the n parameter is 2. Okay, and so it actually, if you were to look at this in terms of a strain rate dependent viscosity, it corresponds to an infinite strain rate. So it's essentially like a plastic case in the limit that these gamma parameters are infinitely big. And so you can see here we've got this is the porosity field. You can see it correlates with this region here where the roughness is significantly decreased. Okay. All right, actually maybe that's enough of those. So in terms of the damage rheology, so one of the things that's interesting, the grain size bands have the opposite polarity to those of the porosity bands, so that's something to look for. Whereas the surface roughness, although that'd be pretty hard to look at, has the same. And you can get the low angle bands, but generally only if the time scale is really fast. So essentially you've just got a strain rate dependent viscosity. Okay, so I'm going to look now at this issue of the orientation of bands in a mid-ocean ridge corner flow. Okay, so this is actually work that was done by my master's student, David Gebhardt. So here we were just looking at linear theory, okay, and we took, again, a corner flow model for flow. Okay, and so what we did basically is we imagined, okay, we've got this a band that sort of starts somewhere down here, okay, and we're going to evolve it along streamlines. Okay, and so we did this for a whole bunch of different streamlines. Okay, so our position evolves with time based on the velocity. We also then have that the orientation of the band evolves with time. Okay, and so what we're doing is we're actually only taking into account the first derivative of the velocity field. Okay, so we're assuming that the bands are sort of on a length scale that's small compared to the length scale on which the flow is changing orientation. Okay, but that allows us to evolve the orientation of the bands in this sort of general way. Okay, and then we then also have then an expression for the growth rate of the bands. This one's valid if we just have purely porosity-dependent viscosity, no strain rate dependent. Okay, so without looking at the evolution, if we can just look at the orientations where the bands are going to grow the fastest. Okay, and so that's what's shown by these white lines here. So we start with bands of all different orientations, and then we look, in this case, just in the flow, at the orientation for fastest growth rate in this flow. Okay, and so similar to what Rich saw in 2006, if you've got a strain rate dependent viscosity that'll produce a nice low angle band, you get them actually oriented fairly nicely in terms of pointing towards the ridge axis. Okay. Similarly, for anisotropic viscosity, we can do the same thing. And in fact, the only real difference you can see here is down here, because it takes a little while to build up the anisotropic fabric. Or there's some deformation required to do that. Okay, but if we look at the amplitude, okay, so we actually integrate the amplitude with time, okay, we get something like this. And unfortunately, as you can see, so the white lines are the orientation for the maximum amplitude. Okay, I've got little green lines on there. So those basically, because some of the cases, the amplitude spectrum was fairly broad. Okay, so to capture the sort of breadth of that, we sort of got, I think it's the plus or minus, I think 50% of the maximum value, sort of shown by those green things. And so generally, though, the orientation is pointed towards the base of the plate, okay, for pretty much all of them. So unfortunately, that means that the bands might not be, or certainly based on this analysis, they're not a good candidate really for channeling melt towards the ridge axis. On the other hand, it means that they might be channeling melt pretty efficiently towards the base of the plate, where there could be a decompaction layer, sort of something similar to the Sparks and Parmentier model of how fluid gets to the ridge axis. So the other thing to look at is how big are the bands by the time they get to different sizes. So that's what's shown in the color is the amplitude. Okay, and we saturated the color if we're starting with a 10% heterogeneity, it would go below 0. Okay, and so one of the things we get essentially is that mostly the large amplitudes really only happen near the base of the plate. So there might only, or it's quite possible that the bands really are only of significant amplitude in terms of permeability perturbation once they're pretty close to the base of the plate anyway. The other thing that has a big effect is that of the bulk viscosity. So the growth rate decreases a lot as you increase the bulk viscosity. Okay, and so if you use a large bulk viscosity, it's hard to get bands that are really significant. Okay, so we would need to have fairly low values or bulk viscosities similar to the shear viscosity. Okay, so maybe I've basically said what I was going to say there. So there's my conclusions regarding that. So now I'm going to move on to, this is some things that are brand new. Now I'm looking at cases where these models are about to fail. So I'm in a sense here I'm looking more at trying to point out how the models are or what would be nice to have models in the future, or how these models are deficient in some way. So this is looking at some of this is from a paper by Holtzman, Kolstad, and Phipps-Morgan, and they're looking at the effective viscosity of one of these experiments. So you can see it has decreased with time. Another paper in that group, they also showed a decrease in the effective viscosity. Okay, and so it'd be nice to see this effect. Okay, so in some of my models, so this is one with had extremely high effective strain rate dependent viscosity from one of these grain size dependent models. You can see there's a little kink. So this pink line is a strain rate marker. Okay, and you can see there is a little kink as you're going across this is the porosity band. This is showing the second invariant of the strain rate field. So there's significant strain rate localization by the end, but only at the very end. So you can see these are the results of some of my experiments. So what I did actually is I integrated, we call it essentially the force that needs to be exerted on the boundary times the velocity. So in other words, the work that's being put into the system. Okay, and I checked that is in fact equal to the volume work going on inside. Okay, just as a check. So you can see that initially, so this is essentially what you get for a constant viscosity Couette flow, right? And so for most of the, and even though there's bands here, there's really lovely, nice looking bands at this time here, you only really start getting significant shear localization right at the end of the simulation, just before it's crashed. So again, pointing out that, you know, the models die just as they're getting interesting, in a sense. So that's something that'd be really nice to, you know, to fix that. The other thing I should point out is that most of these actually got stiffer as a result of the bands forming. Okay, and so essentially the bands, I guess, are not, you know, at a low enough angle. So this is the one that got softer. But the other ones, I guess, were at sufficiently high angle that actually they made the matrix harder to deform. There's another issue, though, there in that the viscosity, like the average viscosity, doesn't stay constant, right? Because the viscosity function isn't symmetric, right? So even though the porosity is conserved, the viscosity actually goes, the average viscosity actually goes up. So if you just do an average of the viscosity of the domain, it also goes up. So that might be affecting this as well. Okay, so another thing, I thought, well, okay, let's look at electrical conductivity. You know, again, you know, this is brand new, and it mostly points out that it'd be nice to have better models. So what I did, though, is I essentially I solved the electrical conduction equation. Okay, I put a constant viscosity on one side, potential, a constant voltage on one side, and another constant voltage on the other side. And I looked at the electrical current flow. So these pink lines now are showing streamlines of the electrical current density. Okay, and so again, for most of the evolution of these things, this is where they're just starting to deviate a little bit from just being straight lines going straight across. Okay, by the very end of this simulation, you can see that the streamlines have, you know, deflected significantly, and they're definitely trying, you know, the current wants to be in these high conductivity bands. And I should point out, I used, to get the conductivity, I assume an Archie's law. Okay, so that the conductivity is just proportional to, in this case, I said porosity to the power 2. Okay, so, so similar to the, you know, effective viscosity case, looking at the effective conductivity. So actually, I should also point out, I did some of these where I put a voltage difference here and here. Okay, and I did another where I put it top and bottom. Okay. And if you look at the effective conductivity, actually in every case it actually went down. These things actually got more resistive as things went on. So again, most of the time nothing interesting happened. It was only at the very end of the simulation where, you know, you start getting significant channeling of the electrical current into these bands. But then I also looked at the anisotropy. Okay, so just dividing, in this case, so the x is the shear plane direction, y is the perpendicular to the shear plane direction. And so you can see, you get some significant anisotropy, and in the direction you'd expect, right, so that the x conductivity is higher than the y conductivity. But again, things are only really starting to change at the very end. So another example where things are just getting interesting and we don't have an answer anymore. Okay, so that's essentially what I've said there. So actually, I'll just maybe talk about some outstanding problems then. So as I've mentioned a few times here, the models crash just as the results are starting to get interesting. I think in my models, it's actually the porosity gets close to 0. Okay, and so similar to what Todd was talking about yesterday, you've got this Darcy law, and so you've got a 0 equals 0 times the pressure derivative, and so the pressure says I can be anything, and it is. So that causes all sorts of troubles. So that, you know, if we're developing tools to fix that, that's pretty exciting. But the other question then, what limits the high end of the porosity, right? So again, this instability doesn't stop when you get close to the disaggregation limit, right? So there's got to be some, essentially the compaction equations just aren't valid, presumably, when you start getting close to disaggregation, right? And so you should stop getting fluid getting sucked into these bands once you start getting up there. And so a good physics to go into these to explain that would be something pretty interesting. Okay, and so longer term problems, the low angle bands, well, we've got some candidates out there. So it seems like anisotropic viscosity is still a good candidate. Another thing that's out there in the experiments is that they seem to show networks of bands at different angles. So, I mean, if you go back to some of my numerical models, you know, you pretty much only have a single wavelength, really. Like, they're all pretty close to the same width, and they're all, you know, maybe slightly different orientations, but in the experiments you see certain bands with different widths, and you definitely see some that are pretty low lying. So there seem to be different types, and we don't seem to see those in the numerical models. So that's something else I think that needs to be explained. All right, that's it. Thank you.
Thank you very much. I see Dave.
In the experiments, you usually see sort of two different scales, where there's
Yeah.
a separation of the bands and then there's the band width themselves.
Yeah.
And do you see that in your numerical simulations?
Not really, no.
Okay.
Yeah, so the distance between is about the same as the width. Yeah, so that's another issue. I agree.
Yeah. I mean, the width between the bands seems to be well correlated with compaction length.
Yeah,
But then the width of the
Of the
band
band itself.
is almost several grains, just a few grains.
it is. Okay. Okay, so yeah, that's...
And that's actually the theory John and I had with sort of this diffuse capillary effect.
Yeah.
It maybe better explain the small
Yeah.
width of the bands, but not the separation of them.
Okay.
But if you're seeing something that looks more like the separation distance, then that's interesting that it's then more controlled by the compaction length than the nonlinear length.
Yeah.
Until you crash.
Yeah, Rich?
I want to comment on the question of formation of bands beneath the mid-ocean ridge.
Yeah.
As you mentioned, it's very sensitive to the bulk viscosity.
Yeah.
And if you think you know what that is, you can run the models.
Yeah.
But there's another approach, which is to say, in the experiments, bands don't form until you get to a strain of about 1.
Yeah.
And if
Yeah.
you just do a scaling analysis on the, and you look at the accumulation of strain along these streamlines, I think you don't actually get to high strains by the time you because there's almost no strain until you start to turn the corner.
Yeah.
And at the corner, then you develop some strain, but you don't really get to 1 within the partially molten region.
Yeah.
So, I mean, I think it merits much more detailed study, but I'd be a bit cautious about saying, that these things can channelize melt, because you can always dial in the bulk viscosity that you need to make that true, but we don't have good constraint on the bulk viscosity.
Yeah, no, I agree. And so I think, one of the things we said is one of our conclusions in that paper was these things are only likely to have a significant permeability variation if the bulk viscosity is sufficiently low.
Yeah.
Although I guess it's interesting if you think about the experiments, though. You see the bands. Like if the bulk viscosity was really huge, I don't think we'd really see the bands in the experiments, right? So at least in the experiments, we need a fairly low bulk viscosity. Whether that necessarily translates to the mantle is another issue.
I suppose the development of bands over a strain of 1 might put some constraint on the bulk viscosity.
Yeah. I think it does, and I think it means, at least in the experiments, it must not be, orders of magnitude bigger than the shear viscosity.
Other questions? Yes, please.
How high was the porosity you got to in your simulations?
Oh, so how high does it get? Yeah, so they started out, some of them I started out with 0.01, some I started with 0.05. So the ones I started with 0.05, some of them, again, just at the point where it crashes, it got up actually well above the disaggregation limit. So in some cases it got up to about 0.6 or something like that.
But you always use the same the same model for the porous media flow.
Yes, other than the changes I talked about. So the different viscosities of the...
As the porosity gets too high, you need to change the model there.
That's right, yeah. And I don't have a change in physics when the porosity gets too high. That's correct, yeah. Yeah, Garrett?
Alternatively, how low does the porosity get in the lab?
Oh,
Do they know that?
that's a good question. I don't know that off the top of my head. Rich, do you remember?
I think, less than 1%, but not less than 1/10 of a percent. But
Can they say
They resolve.
between the bands? Can they say it gets to 0?
I mean, in between the bands.
Yeah.
In between the bands, it gets very. I don't know. I just thought it would be very much lower than 0.1 or 0.01.
Andy?
You showed an anti-correlation between melt fraction and grain size in the model. What was the role of melt on grain size? Was it acting as a pinning phase or no direct interaction? Maybe comment on that, please.
So the melts on the grain size. I'll have to go, actually probably John or Dave are actually in better situations to answer that.
Yeah, it sort of acts as a pinning phase.
Okay.
Or maybe ask how sure are you of that role, because the opposite suggestion is that it acts as fast diffusion pathways and should enhance grain growth.
It really does depend on the solubility of the solid, between the solid and the melt. I mean, if the solid is soluble in the melt, then it should be more like possible ripening and less of a pinning phase. So we sort of assume that they were immiscible. If they're pinning, you have to assume that they're really immiscible.
If you play with alpha, does it change the wavelengths that you said?
In the linear theory, no. Right. So with the alpha parameter, all it would do was just change the magnitude of the growth rate. On the other hand, though, if the growth rate is very small, then the bands will have to get evolved a lot longer before you start getting a significant amplitude, and so that will change. It'll change the amount that they've been sort of rotated, and so that potentially would change sort of the I guess the longer they get rotated, the closer they get to sort of that fraction of the compaction length that I talked about, at least for my mechanism for the increase in the band wavelength.
Okay. You have another question right there?
I was wondering, is there so if you go to 3D system, is there a process that limits the third dimension of the bands, or should they be sort of infinite?
Okay, yeah. Yeah, I did a little work trying to model in 3D, and then I kind of gave it up. I wasn't getting high enough resolution. I think in the experiments they do show a few where they've actually cut in both, at least, sorry, in terms of the simple shear where you've cut in both directions. And they're fairly 2D if I recall correctly. So they're fairly extensive in the, into the plane direction.
Julian, do you
Yeah,
want to?
so I did.
Oh yeah, you've done
like
that.
in the strain rated biology, the shear bands in 3D, and that's exactly what I see. So I see they get like two-dimensional.
Okay. Yeah.
Maybe one last quick one. Yes.
Very simple question. Many people talk about the angle of the shear band. If you imagine a very old oceanic atmosphere where flow is horizontal, do you expect tilted melt bands to exist if you have a gravity?
Okay, so in terms of gravity, I guess my results seem to show that you would still get there's no problem with still having melt bands if you've got gravity and buoyancy.
And melt stays there in a tilted.
And yeah, they maintain their orientation. They just travel along as waves, but with that orientation.
No convection?
Well, it's a compaction effect that's driving the waves, and then that would be creating it. Yeah.
Let me try to interpret. I think that if you didn't supply from more melt from below,
right? What I mean.
Then they would drain, and in fact they drain even faster because of the vertical orientation of the bands. So I think it's hard to maintain bands, especially when they're oriented like that.
Well, if they're sheared at 20 degrees, will they still drain fat? Because then they're oriented
variability.
wrong for drainage, right?
Yeah. I don't know, or maybe they move like porosity waves. But I think there's something that done there.
All right. I think it's time for lunch, and we will reconvene at 2 o'clock as usual. And let's thank again.